Today we are in Unit 4, Lesson 6. This comes from Chapter 12 out of the textbook. And the topic of this lesson is circular and periodic functions. We're going to start off with a concept for how you graph functions or how you think about functions that are part of the unit circle. So the concept here says that if the terminal side of an angle theta in center position intersects the unit circle at some point with coordinates x comma y, then the x coordinate is the cosine of the angle theta and the y coordinate is the sine of the angle theta. And in symbols, this says the point x comma y is the same as the point of cosine theta comma sine theta. So for example, if your angle theta was 120 degrees, the way you'd find the coordinates of that point is you'd find the cosine of 120 and the sine of 120 and then graph the point. And you can see that in the picture over here. So the first example is going to use that concept. It says that we need to find the sine and the cosine given a point on the unit circle. And the problem says the terminal side of angle theta in standard position intersects the unit circle at the point square root 7 over 4 comma 3 over 4. And we need to find the cosine of theta and the sine of theta. And this is actually going to be a really simple process. Basically, you're just looking at the x part of the point, and that's the cosine, and the y part is the sine, and you're just going to pull the value that they give you. So the cosine of theta is square root 7 over 4, and the sine of theta is 3 over 4. Really simple, really straightforward. Here's one to go ahead and check your progress on. Pause the video, figure out the answer, and in a second I'm going to advance to the next slide and reveal the answer. And the answer, of course, this time is A. The cosine is square root of 15 over 4, and the sine is negative 1 over 4. Example 2 is talking about how to identify the period of a function. We're told to determine the period of the function that's graphed here in this slide. Basically, the concept of the period of a function is when does the function start repeating the pattern that it's making. So if you follow along the graph, you can see we start at the origin. We go up, stay even, we drop down, come up, stay even, drop down, boom, boom, boom. And then the next time that we get back to the origin is at pi over 3. And if we start from pi over 3, you can see that from pi over 3, we're following the same pattern that we did at the beginning of the graph. And then we come back to the x-axis again at 2 pi over 3. And then the pattern repeats again, boom, boom, we end at pi. So we have 3 full periods of the graph before we get to pi. 1 full period ended at pi over 3. 2 full periods ended at 2 pi over 3. 3 full periods ended at 3 pi over 3. The period on this function is pi over 3. Okay, here's one to check your progress on. Go ahead and figure out the period of this pattern, the period of the function. I'm going to pause the video, figure out the pattern, and then we will see the answer on the next slide. And the answer this time is pi is the period. You can see that we start at -1, go up to 1, come back to -1. Then we repeat, -1, up to 1, back to -1. So this pattern took until pi to complete 1 full cycle of the period. All right, example 3 is a real-world problem. It's about cycling. It says the pedals on a bicycle rotate as the bike is being ridden. The height of a bicycle pedal varies periodically as a function of time, as shown in the figure. Notice that the pedal makes 1 complete rotation every 2 seconds. Make a table showing the height of a bicycle pedal at 3, 3.5, 4, 4.5, and 5 seconds. So I'm going to come back here and look at the graph that we're looking at. So at 0 seconds, we're at the top. and then we make one full rotation at 2 seconds. So we'd be over here at 2.5, here at 3, 3.5, 4, 4.5, 5. So basically we're graphing the heights at those values. Starting at 3, so one full rotation is 2 seconds, we need to go one more second. So we'd be starting our graph at 4 for the y value, and then just moving incrementally around the circle at the height specified here. And so here is the table that represents that period. We started at 4, up to 11, all the way up to 18, back down to 11, and then back down to 4 at 5 seconds. Part B says we need to identify the period of the function. So the period is how long a graph takes to make one complete rotation. And just by looking at this, the way it's labeled, you can see if we start at 0 seconds, we're at the top, and then we're back up here at 2 seconds. The period, therefore, is 2 seconds. Okay, part C of the problem says that we need to graph the function, and we're going to let the horizontal axis represent the time, t, and the vertical axis will represent the height, h, in inches that the pedal is from the ground. So basically we're just graphing the points that we came up with in part A of this problem. When you make the graph, it's really important, I'm not sure if it's super obvious here, but it's really important that you curve your graph as you get to the minimum value and maximum value. Don't make these perfectly straight lines. Don't make them V-shaped. You want to make them more U-shaped. So they're going to be curving as you move through here. This is not a hard angle right here. It's more of a curve. So you can see at 3 seconds, we were at a height of 4. We moved up to a height of 11, moved up to a height of 18, back down to 11, back down to 4. And then also it's important that you show that the function keeps going. So you draw arrow tips on the ends of the period that you drew for the function. That this is not the only section of the graph that you draw, that you imply that the graph keeps going in both directions. Okay, here's a real-world problem for you to check your progress on. It's a very similar concept. I'm going to pause the video, give you time to read through the problem, and then we'll head over to the answer on the next slide. All right, the answers. Here are your options. If you need to go back and look at the graph again, these are the 4 choices. We're going to see the answer on the next slide. And our answer this time is choice B. At 0 time, the height was 30 inches. And you can see it takes, how long does it take, actually, to get back to a height of 30 inches? That's probably going to be part B, the period. Okay, go ahead and we'll see the answer on the next screen. The period, of course, this time is 4 seconds. You can see it starts at the top at 0 seconds and gets back up here at 4 seconds. Choice C says that we need to choose the correct maximum and minimum height of the function. And this should be pretty simple, just looking at the data provided over here. We're going to go ahead and see the answer on the next slide. And our answer this time is D. Obviously the maximum that the pedal will ever get to is 30 inches. That's the highest point on the circle, and the lowest it will ever get, minimum value, is 10 inches. That's the lowest it ever gets on the circle. Okay, example 4, we're going to be evaluating trig functions, and we've actually already done a little bit of this in class by looking at the unit circle already in Unit 4. But this one says that we need to find the exact value for the cosine of 690 degrees. And the first thing that you're going to want to do with this is notice the fact that it's more than a full circle. So you want to find the coterminal angle with 690. And you can do that by subtracting 360 degrees, and you would get 330. So the cosine of 690 is the exact same as the cosine of 330. And then just by looking at the unit circle, the cosine of 330 is the x coordinate value of the point at 330 degrees, which is the square root of 3 over 2. Part B, we're going to find the exact value for the sine of negative 3 pi over 4. And again, you want to work off coterminal angles. It's always easier to do positive angles than it is negative angles. And so when you're working in radians, you need to think about that a full circle is 2 pi. But because we have a denominator of 4, we're going to need to convert 2 pi to be something over 4, which in this case would be 8 pi over 4. So negative 3 pi over 4 plus 8 pi over 4 gives us 5 pi over 4. So the sine of negative 3 pi over 4 over here is the exact same as the sine of 5 pi over 4. And then you just need to find the 5 pi over 4 angle on the unit circle. Find the y coordinate value because we're looking at sine. And the y coordinate value at 5 pi over 4 is, of course, negative square root of 2 over 2. Okay, lastly, we're going to look at a check your progress problem for example 4. We're finding the cosine of 660 degrees. Go ahead and pause the video, work it out, and then we'll see the answer on the next slide. And our answer this time is 1/2. Cosine 660 is the same as the cosine of 300 degrees. And the cosine of 300 is 1/2. For part B, we're going to find the exact value for the sine of negative 7 pi over 4. Go ahead and work out your coterminal angle, find the sine value, and then pause the video and we'll see the answer on the next slide. And our answer this time is square root 2 over 2. The sine of negative 7 pi over 4 is the exact same as the sine of pi over 4. Pi over 4 being in the first quadrant means your answer is going to be positive. Answer is square root of 2 over 2. And that brings us to the end of the Lesson 6 video for Unit 4.